Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about simple harmonic motion. And as the name suggests, it is simply a beautiful phenomenon that connects to all sorts of phenomena in the world. We'll consider in this course simple systems like masses connected to springs that oscillate back and forth in simple harmonic motion. But the basic ideas extend into all realms of physics, from waves on the surface of a liquid to the most esoteric ideas in string theory, which is at the forefront of modern physics. So let's dig in. So we can begin our discussion of simple harmonic motion, discussing something that we just finished discussing, namely rotational motion or circular motion. So what I want you to consider is a point indicated by this yellow dot that can move around a circle of radius. We'll call the radius A now for reasons that will become apparent. And so the angular position of the yellow dot is indicated by this angle theta as before. And we imagine that the object is undergoing uniform circular motion, which means it's moving at a constant angular velocity omega. So if it's moving at a constant angular velocity omega, that means theta as a function of time is increasing linearly. It's just omega times t. And then to make the discussion more general, we can add in an arbitrary constant, which we'll call phi, which is simply the value that theta has at time t equals 0. And as you know, circular motion like this is periodic. It repeats itself with a period t, and the period t of the motion is related to this angular speed or angular velocity by the simple relationship that the period t is just equal to 2 pi over the angular speed, because omega times the period has got to equal 2 pi radians, because in one period of motion, the angle theta changes by 2 pi radians. So to connect our discussion of circular motion, rotational motion, to simple harmonic motion, let's introduce these coordinate axes here, the x and y coordinate axes. And let me make them a little bigger. And what I want you to imagine is, our yellow dot is going around the circle in uniform circular motion. Theta of t is increasing linearly over time. But now let's focus on the x and y coordinates of this yellow dot and how they vary as a function of time. So, for example, to get the x component of the yellow dot, I just need to project onto the x-axis. So the x component at any time t is just given by the length of the radius of the circle A times the cosine of this angle theta. In other words, we can write that the x-coordinate of the yellow dot as a function of time is just equal to A times cosine of omega t plus phi. And similarly, the y component, that's just the side of this right triangle here opposite the angle theta. So the y component of the yellow dot as a function of time, we can write as A times the sine of omega t plus phi. And we are going to call this kind of motion where the position varies as either in proportion to either the sine or the cosine of omega t plus phi. We're going to define this as a type of motion that we're going to call simple harmonic motion. And to see what that looks like visually, let's look at the following little video clip. So here's my little yellow dot, and it's mounted on a turntable. A turntable is a device which used to be used to play some things called records, which some of you may have heard of. So when we turn on the turntable, the yellow dot will rotate in uniform circular motion. There it goes, around and round and round it goes. A little bit slower than the 33 1/3 revolutions per second. But let's look at the y coordinate. We now have a side shot. And if we just focus on what the y-coordinate of the yellow dot is doing, you see that it's oscillating back and forth. And that kind of motion is exactly the kind of motion that you get, for example, when you hang a mass on a string and let it oscillate up or down. Similarly, if we focus on the horizontal component, the x component, we see it's doing something similar. And as you will see experimentally in lab before too long, that kind of motion is easily, at least approximately, replicated by a pendulum swinging back and forth. So these kinds of motion that we've defined mathematically as simple harmonic motion are easy to realize in the actual world with simple things like masses on springs or pendula. And it's useful to make a graph showing what these functions x of t and y of t look like as a function of time. So to make things simple, I'm going to assume that in this graph, we'll set this constant phi equal to 0, and you see that the red curve represents x of t. It's a cosine function. A cosine at time 0, the cosine of 0 is 1. So at time 0, the x of 0 is going to be equal to plus a. And the the function is going to go through one full cycle of its motion in a time period t, and again, t is simply related to this constant omega by 2 pi over omega. So we now that omega is appearing in this expression for something that's oscillating back and forth, we now don't refer to it as the angular speed or angular velocity anymore. We're going to call this the angular frequency of the motion. So omega in this context is called the angular frequency of the motion. And it can be a little bit confusing because we're using the symbol omega in both discussions of simple harmonic motion and rotational motion. We use the same symbol because, as we've just seen, the two ideas are very closely linked, but nonetheless, it is a source of confusion when you use the same symbol to mean two somewhat different things. So be aware of that. And then I've also graphed in the blue curve here is how the y component of the yellow dot varies as a function of time. At a sine function, we recall, at time 0 is going to have a value of 0, and it's going to also oscillate between plus and sine goes between plus and minus 1. So the blue curve ends up oscillating between a maximum value of plus a and a minimum value of minus a, but it's just sort of out of phase with the red curve. We would say they're 90 degrees out of phase with one another. So as the video that we watched suggested, we can build physical systems that undergo simple harmonic motion just by doing simple things like connecting masses to springs. So let's see how that works. So I want to build a system, a physical system, whose x-coordinate will vary as a function of time in a manner described by this function, this cosine function. Well, that's simple as it turns out. What I'm going to do is I'm going to build a little tabletop with a wall at the end, and then I'm going to connect to the wall a little spring, and the spring will have a spring constant K, and I'm going to attach to the end of the spring a mass M, and I'm going to choose a frictionless tabletop here so that the only horizontal forces that act on the mass is the spring force. And let's build a little x-axis here. So I'm going to call the horizontal direction x, and I'm going to make the the relaxed position of the spring where it's not exerting a force. I'm going to call that x equals 0, and then we can either stretch or compress the spring, and we'll assume it's an ideal spring. So the force that is exerted on the mass is just equal to minus k times x. And now let's consider what Newton's second law has to say about all this. Newton's second law says that the force that is exerted on the mass in the horizontal direction must be equal to the mass times its acceleration. And of course, we can write the acceleration as the second derivative of the position with respect to time. And since the force is equal to minus kx, that means that for my mass on a spring in the horizontal direction, we can write the following equation. Minus kx is equal to m times d2x dt squared. Or rearranging, I can write this as d2x dt squared is equal to, and so x for a mass on a spring, we expect it to be, they're functions of time. So the idea is that what Newton's second law tells us is that however x varies as a function of time, at all times t, this equation must be satisfied. This thing that we just wrote down, by the way, if you don't know, is an example of what is called a differential equation. Differential equation. And that just means that it involves derivatives. So when we talk about finding the solution to a differential equation, what it means is we're trying to find a single function, x of t, that when we plug it in on both sides of this equation, the left-hand side and the right-hand side are always equal to one another at all different times t. So what we're looking for is a function x of t such that when we differentiate it twice with respect to time, we get a quantity which is equal to minus some positive number times the function itself. So you're looking for a function that when you differentiate it twice, you get something proportional to the function itself. Now, can you think of a function that satisfies that? That's right. Sines and cosines have the property that when you differentiate them twice, you get something that's proportional to where you started. So let me show that explicitly. So we've already suggested that this kind of simple harmonic motion, this kind of function here, is going to be a mathematical description of how a mass on a spring moves. We saw that sort of experimentally in the video clip that I showed. So let's prove mathematically that it actually works. So if we have a function x of t of this form, so that is, let me write it again, if x of t is equal to a cosine omega t plus phi, then what's dx dt? I want to calculate the first derivative. I need that in order to calculate the second derivative. So dx dt, when you differentiate cosine, you get a sine, but with a minus out in front. So the derivative of x with respect to time is minus omega a times sine omega t plus phi, where I used, remember the chain rule here is when you differentiate, since the thing inside parentheses has this omega in front of it, you pull out a factor of omega when you take the derivative. And if that's dx dt, then to find the second derivative, d2x dt squared, I just have to differentiate the first derivative one more time. And now I'm taking the derivative of a sine, and the derivative of sine is plus cosine. And again, I'm going to pull out a factor of omega due to the chain rule. So what I get is the second derivative is minus omega squared a times cosine omega t plus phi. Aha, notice that as we were looking for, the second derivative is equal to minus something times the function itself, times x of t, because we recognize that this part here is just x of t. So for this particular x of t, it's true that d2, the second derivative with respect to time, just gives you minus omega squared times the function itself. So we were looking for a function that would satisfy this equation. This is the equation we got from Newton's second law applied to the mass in the spring system. We guessed that a function of this form would do, and we showed that if you choose a function of that form, it works, provided omega squared is equal to k over m. That's the only thing that we need to get it to work. And that means basically that we were going to require that omega squared equal to k over m. And what that tells you is that the angular frequency of a mass on a spring is just given by this relationship here. The square root of k over m tells you the angular frequency of a mass on a spring. And it's also very useful to write down what the actual frequency is. The actual frequency is the number of full oscillations per second. Omega is the number of, is 2 pi times that. So if you divide omega by 2 pi, you get the actual frequency of the motion. And what the takeaway from this is that if you have a mass on a spring, the frequency at which it oscillates back and forth, the number of times per second, just depends on the value of the spring constant and the mass. So if you have a stiff spring and a light mass, you're going to have a high frequency of oscillation. So things that are light and stiff oscillate back and forth very quickly, and things that have a floppy spring and a lot of mass are going to oscillate back and forth much more slowly. Okay, one quick but important example of simple harmonic motion, or at least approximately simple harmonic motion, is a pendulum. And you're going to experimentally make measurements on the system to measure the period of a pendulum experimentally with your lab kits. So let's see what theory has to say about the period of a pendulum. So the pendulum, a simple pendulum, just consists of mass, point mass of a mass m, and it's suspended from something, maybe the edge of a table. The length of the string connecting the mass to the table edge is L, and the angular position of the mass is given by theta. And this is a great system to try out our knowledge of torque and the rotational inertia and the rotational form of Newton's second law. Because if you think about a pendulum, you're really rotating about a fixed point here. So let's write down the rotational analog to N2 for the case of a simple pendulum. What the N2 says is that the angular acceleration of the pendulum is just given by the ratio of the torque on the pendulum to its rotational inertia. And what's the torque on the pendulum? Again, when you talk about torque, you have to say what you're measuring it with respect to. So the torque on the system, you have to look at the forces that are exerted on the mass. There's a string force, but that is not going to exert a torque since, if you're measuring with respect to this point, the R vector points in this direction, the tension force points in this direction. There's 180 degrees between them. There is no torque exerted by the string. The only thing that exerts a torque in this system is due to the force of gravity, which points downward. So what you should convince yourself of is that the torque due to gravity is minus mgl times sine of theta, because a torque is a force times a distance. So the force is the force of gravity. The distance, the R value, is L in this case. And you need this sine of the angle between the force and the R vector to get the torque. And that angle, you should convince yourself, is exactly theta. And we need the minus sign here because the torque acts as to restore the pendulum back towards theta equals 0. So if theta is a positive quantity, the torque is going to act in the opposite direction to try to move the pendulum back towards this equilibrium point. So that's the numerator here. And then the rotational inertia of a point mass is, in this case, is simply ml squared. So Newton's second law, there's obviously some cancellation here. The m's go away, and this L cancels with one of the factors of L in the denominator, and we have that the angular acceleration of the pendulum is just equal to minus g over L times sine theta. In other words, the angular acceleration we can write as the second derivative of theta with respect to time. That's just equal to g over L times sine of theta. That's looking a little familiar. Look how similar this equation is that we wrote down for the pendulum to the equation that we wrote down for the mass on a spring system. They're really of a very similar form. The name of the dependent variable is different. One's theta and the other is x, but what's in a name, a rose by any other name would smell the same, I heard someone once say. So we've got a second derivative on the left, and then we have minus some constant. It's not quite the same. This is theta of t here. So the problem is that we've got not just theta of t here, but sine of theta of t. Bummer. They're not quite the same, but not to worry. You may recall that for small values of theta, and when I say small, I mean small compared to 1. When theta is small, is measured in radians, the sine of theta is very nearly equal to theta itself. And if you don't believe me, take out your calculator, set it to radians, and put in a number like 0.1 and take the sine of it, and you'll get something very close to 0.1. So if we're willing to make the approximation that theta is small compared to 1, then for the pendulum, it should at least be approximately true that the equation that governs its motion is really mathematically identical to the equation for a mass on a spring. And that is really good news because we already know, for example, what the angular frequency and the period is of this motion. The angular frequency is just the square root of this constant that appears out in front. Remember, we wrote in this case that omega was just equal to the square root of k over m. So without doing any additional work, we know that the angular frequency of a pendulum is equal to the square root of g over L, and the period of a pendulum is just equal to 2 pi over omega. So that's the period should be 2 pi times the square root of L over g. So we have a very explicit theoretical prediction that you can test experimentally. The prediction says that the period of a pendulum should depend only on its length, and the g, which we assume is pretty much the same for everybody who's going to do this experiment. And you can test this. You can have with your Arduino and PhotoGate, you can measure the period very accurately, and you can check to see whether this relationship is true. And then another thing that's worth noting is this relationship makes a prediction that the period shouldn't depend on the amplitude of the motion. So you take your mass and let it go, and no matter how much theta, how big it is initially, it's going to swing back and forth, and the period should be the same. Well, except we made this approximation, so it may not be exactly the same. But that is exactly the issue that you're going to investigate experimentally. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye-bye.